Thank you. Do you don't have homework for you now?
Yeah, it's just a big pile of
Chemistry, physics.
like chemistry, but like random worksheets.
Wednesday? Yeah, okay.
I needed, I think yesterday was my chemistry.
Yeah. Yeah. Okay. Any other time and day you can?
Tuesday. So
Next Tuesday.
Tuesday.
Yep, I think we got some paper printed.
Um,
Yep.
how do you do the homework, the one with the compression factor there? Oh, it's like on the left hand.
What page was it? Page 6?
Yeah.
Finish that. Finish that. I have some other like Skittles or other jellies, but need that tub. Okay, question 4. Ideal gas law. Gas is one of for which the ideal gas equation P equals nRT applies at all the temperature and pressure. In reality, no gas is perfectly ideal. If the gas behaves in an ideal way, PV would always be equal to nRT. PV and nRT are the same. Then if you do PV and nRT, and so it would be supposed to be 1. The expression period is called the compression factor. Okay. Scientific skills. If we plot the compression factor at the pressure at all temperature of the gas are varied, the resulting curve should be a straight. All right, okay. Horizontal line showing compression factor of the 1, but if the gas does not always act in the ideal way, the curve will not be straight. Okay, yeah, all right. The graph will plot the compression factor of the nitrogen gas as the pressure is increased at different temperatures. Okay. So for a temperature of 300 Kelvin, describe what happened to the compression factor as the pressure increases up to the 200. So 300 Kelvin, 200. And it's just the reason why that might be the case. So for 200 Kelvin, 300 Kelvin, okay, it's kind of going up all the way, the pressure. Right. So ideal gas law is actually coming from like the idea that this is working ideally. But as we know, like everything's not working ideal at the time. So that's giving you some case like what if we have some ideal situation there, everything's controlled well, and then therefore, sorry, a little bit down. So we call that ideal like in a situation when the PV equals nRT. This is more like physics term, by the way, so rather than the chemistry, but let's go through that. That means when this is 1, we call this an ideal situation, but practically we will not get the ideal situation all the time. So what you see there here is you get the ratio of the PV equals nRT, and you have an independent variable of the pressure that's increasing that. So for 300 Kelvin, what the trend is, there was no increase of the PV equals nRT for the given temperature, but just slightly going up in here. Now remember that the temperature is constant. Okay, same for the N and R. So N and R, and the P is the variables there. They are constant basically. Because we can't change the number amount, we can't change the R value. So if this N is constant, R is constant, T is constant there, then the only affected variable would be P and the V. What that means is this graph is representing that what happened to the volume as we increase the pressure. So what we get, this is why we call the compression factors, because what we know is as you compress the gases down, you can increase the pressure and they will affect the volume as well too. So as the pressure increases up to the 200 at the temperature, such as a reason why this might be the case, the compression factor is getting increased. Why is that? Because we can just go here. The P is equals to 1 over V, if that's a constant values too. This is kind of giving us that the ratio, like what is this relation? B, VP, according to Boyle's law. This is actually using the Boyle's law, that as we are increasing the pressure, the PV equals nRT factor is getting increased, means that this greater compressions are occurred in that given situations, so that's increasing the factor. That's how we can describe for the question A. B, describe what happens to the compression factor as the pressure increases above 200 bar at the room temperature, which is 25, such as why this might happen. We're expecting that if the pressure increases at 200 bar in the same, like if everything's kept a constant, then according to Boyle's law, that pressure is increased, then volume must be decreased then. Or in a way, you can think about you're compressing the volume, compressing the gases down, of course, like increasing the pressure, of course, to decrease the volume in that case. So that's a question B. According to Boyle's law, as the pressure is getting increased to 200 bar, which is kind of double of what we're in now, the volume would be decreased. That's as volume and pressure are inversely proportional. But this is actually, as I said, like some questions we have physics related, but it's good to think about. See what happens to the compression factors at the temperature below room temperature as the pressure is increased up to 200 bar. Guys, I know the temperature 100 Kelvin, 200 Kelvin, 300 Kelvin is quite intimidating because they're really big values. But remember that the room temperature or the 0 degrees Celsius is 278 Kelvin. So these 200 Kelvin, this 100 Kelvin are extremely cold temperature. That would be like minus 178 degrees Celsius. That would be like minus 78 degrees Celsius. Only be like a 300 Kelvin is somewhere where we're close to the room temperature then. So you can make think this is a room temperature, around room temperature. 200 Kelvin would be, in our understanding, it would be minus 78.15 degrees Celsius. This would be minus 178.15 degrees Celsius, so extremely cold. And what happens to the extreme cold temperature is they are not going on to the gaseous state a lot because the heat energy is kind of taken off. Don't worry about this for now, but that's, as I said, it's more about physics. The heat energy kind of taken off from the particles, so they're, even though they want to go out, they're going to want to get dispersed from the high pressure, they can't because it's extremely cold. They just, it's like same as you, like if that's really cold outside, like minus 25 degrees Celsius, would you go out? You'd be like, no, I'm going to stay home and nice and warm. I'm not going to go out. I don't care what happens. I'm just going to stay inside until you get more pressure from your mom. Then you have to go to school. So mommy is like a pressure. You get a pressure from your mother. They say, you need to go to school. I know, but it's cold. But still going to go to school. You're going to delay of that until you get a pressure that you can't hold anymore. So you're going to go. The same thing happens in the gases too, the particles. What we see there is PV equals nRT getting decreased, means we get a less compression. That's due to the temperature. Basically, all the heat energy of the particle are taken off. No energy to move until you get the pressure from your mother pushing you physically. Okay, until you get the pressure that is making you physically move. That's the starting of the bouncing back. A little bit of the scientific skills required to interpret that, but more about physics rather than chemistry, to be honest. This is using the kinetic model of the particles. But does it kind of make sense to you? Like, kind of give you some understanding about the questions? Don't worry too much about it. You won't get that question. Let's get straight. No, you won't get these questions. But you will get these questions now. So let's start these worksheet 1, 2, 3, 4, and 5. Could you pass that around? You may need some formula sheet for this question. Thank you. 2, 3, 4, 5. Can you pass that too? One for you, one for you. All right. I'll give you about 20 minutes. I would like to try this question 1, 2. And maybe up to 3 if you can. We're gonna finish up to 3 for now. So question 1, 2, maybe up to 3. We're gonna finish up to question 4 today, if you can. I'll probably go for 5, depends. But try for 1, 2, and 3 for now, please. So 1, 2, and 3, please. You remember? I think it's just a test.
Yeah,
It's just a test. No, like depth study whatsoever. Yeah.
I don't know why it says depth study.
It's an in-class task. It's gonna be a test. How long is your period on the Tuesday?
Tuesday, like 65, 60 minutes.
60 minutes, a 1 hour test.
Yeah.
Yeah, it's gonna be 1 hour test. Maybe 50 to 1 hour. Then. All right, and just the whole module 1 contents.
Yeah, they say there'd be more of a skills test, but like a module test.
It'll be limited in how much I can put it in. Like, there'll be a couple of graph questions, and that study for some ionization energy, the trend graph, and that's possible. Periodicity, definitely you gotta get that. Skills as in like you may need to draw a Lewis dot structures.
Oh,
Yeah.
but we haven't even got those yet.
Oh, okay.
We just started periodicity.
Okay. Yeah, probably get covered by then. I hope. Methods of the separating the mixtures. So those questions that we're kind of practice in the class. So, do you want me to reprint that test paper for module 1 so I can practice again? Yeah. I have a few in module 1 test paper. Yeah, I think it'll be good. I'll give you one set this week. So let me know if you need another set of the papers to practice, probably the week after. No, 11th or 11th? No, it wasn't 11th. 9th. Okay, that's a week 11. So this and next week. So try to do 2 sets. I can also give you some answers with that, so you can practice that.
How do we convert mmHg to kPa?
Which one? The millimeter mercury? Remember the millimeter mercury is equals to the 1 over 100, 100.13 atmosphere. Hang on, let's just. It's easy to forget that one. Yep, so 1 atmosphere is equals to 1 over 760 millimeter mercury. In other words, 1 millimeter mercury is same as 1 over 700, 700. No, sorry, 760, I should say. 760 millimeter mercury. So that's a 760, the ATM. And as 1 ATM, atmosphere is equals to the 101.3 kilopascal. We can substitute back in here that 101.3 kilopascal is 760 millimeter mercury. So 1 millimeter mercury must be 101.3 divided by 760 kilopascal. This is how we can convert the millimeter mercury to the kilopascal then. But do we need to convert that? Okay, we'll see. think I'm getting some. Oh, okay. Ria, well done. Christine, Ashley, Ara, that's chapter 3. Then we're getting some homeworks back as well too. And Jenny. Perfect. No name. No name. Ashley Gong, Jean. All right, shall we have a look at question 1, 2, 3 now? Question 1. 10 liter of argon exert the pressure of the 1.05 times 10 to the power 5 Pascal PA at 27 degrees Celsius. Calculate the mass of the argon present. So what we have to think from the given unit, the pressure is 1.05 times 10 to the power 5 PA is given. You need to get that into the standard unit of the kilopascal, because to find the number of moles, we have to use the ideal gas law, and as we got the number of moles, then we can convert it back to the mass. So that is 1.05 times 10 to the power 2 kilopascal by times 10 to the power minus 3. Temperature is 27 degrees Celsius. Remember that to convert it back into the some units of the Kelvin, that are giving you 300.15 Kelvin then. Okay, what else? We're given that 10 liters. The volume is given at 10.0 liter too. So bring it out, the PV equals to nRT, or we can just go like N equals to PV over RT, like that. Substituting all the values, the N is then equals to P, that 1.05 times 10 to the power 2 times the volume, 10, divided by our 8.314 gas constant times the T as a 300.15 like this. I'll just leave it at the exact value for now because there's given number of moles, and then what I can do, the M of the argon can be found by N times the molar mass, which is showing that 1.05 10 to the power 2 times 10 divided by 8.314 times 300.15 times the molar mass of the argon, that is 39.95. Looks complicated, but you can just put that in your all the values in your calculator straight away. Then you'll get 16.8 grams for A. Good. B. The gas is allowed to expand to 20 liters, and the pressure falls to the 6 times 10 to the power 4 Pascal. Calculate the new temperature of the gas. All right. We do not need to use ideal gas law for this kind of case, because you're given some other gas factors are constant. You only get a change of something. So this is a time that you use the combined gas law. So according to the combined gas law, that P1 V1 over T1 is equals to P2 V2 over T2 here, like that. For this kind of ideal, except the ideal gas law, all other gas law, you do not need to convert the unit to save it. So you can just keep that unit of the Pascal if you like to. It just doesn't really matter for this. We need to find new temperature. So T2, new temperature is P1 V1 over T1 times that, the 1 over P2 and the V2. Does it make sense? So let's get that. P1 we used to have, let's leave that to the Pascal value. It doesn't really matter for now. 10 to the power 5 times the V1, that's what used to be 10 liters. Used to be the temperature of, you can even leave that to the temperature 27. You don't need to convert the units because we got to find in the temperature anyways. That times that P2 that we had is given as 6.00 times 10 to the power 4. That times that, the volume 2 is a 20. Then you should get the temperature of 69.8 degrees Celsius. This is some at the same 342.9 Kelvin. It's kind of equivalent answers. Okay, so you need to understand like when to use the ideal gas law, when to use combined gas law, when to use the other gas laws too. The ideal gas law is really quantitative. In other words, you're able to find some of the factors missing by counting that all the gas factors. You can use the combined gas law, but for those kind of using the ratio values, if you have some changes, this is the key. If you have some changes in the gas factors, you might need to consider using the combined gas law or any other gas laws, because that means that other gas factors are kept constant. Does that make sense? C. A further 10 grams of argon is added to the gas from part B. Calculate the new pressure of the gas if the other conditions from part B are unchanged there. So let's count from the mass of the argon added. That's given at 26.8 grams. Means N of the argon added must be a mass over molar mass. That's a 26.8 divided by, given the 39.95. You would get approximately 0.671 mole. This amount of the mole is now added. On the top of that, this amount over here. Then time to bring it out to the ideal gas law again. The P from the PV equals nRT can be recalculated by the nRT over the V given as that. Now the value we had, 0.671. Counting that, 342.9. If the other condition part B was unchanged. Okay, we got to recalculate that value. So what we know, the N is adding up these values, so you got to actually need to calculate the value in 1.05 times 10 to the power of the 3 and divided by 8.314 times 300.15, approximately giving you 0.421 mole from the previous answer. So N would be 0.421 plus 0.671 for total number of moles times that 8.314 PV, okay, and then times that. Now temperature what we have in the question B, that's given as, we found at 69.8 degrees Celsius. Find that in 69.8 plus 200 and keep forgetting that value. 73.15, you'd get 342.95 Kelvin, so times that, 342.95 divided by, the volume is now given as 20. As you do so, you'd get the pressure in the kilopascal would be 95.6 kPa then. No, it's not really, like there should be those different values. So 0.421 plus 0.671, let's recalculate that. Times 8.314. Yep, 155, sorry, 156 kPa in 366. This would be the final answer then. Question 2. Of the total, which is 10 grams. added.
But then you calculated it 26.8. Like with the added.
Oh, I did that. Oh, sorry. I did that. Okay. I was like, why is this so value so big? Okay, yeah. Sorry, that means you're right. This is should be just 0.671. I re-edited it. So that means, yeah, it would be the previous value, 95.6 kilopascal there. Yep. Yep, because we added a 10 to the 16.8. Yep, mistakes. Good. Question 2. That's you. Nitrogen 2 oxide NO can be prepared by reacting copper with the 7 molar nitric acid. So the reaction is given as 3 copper reacting with the 8 nitric acid, producing copper nitrate, nitrogen nitrogen dioxide, monoxide gas, and H2O. So A, what volume of the NO at 18 degrees Celsius and 99.85 kilopascal pressure will be produced if 2.2 grams of the copper are reacted with the excess of nitric acid? So when the question is giving you that we have an excess amount of the reactant, means we don't have to worry about any of the limiting reagent. We're just going to purely thinking about amount of your copper given. So start from the number of the copper, first of all, and of the copper, founded by mass over molar mass. That is, you're given 2.2 grams. That divided by molar mass, which is copper is 63.55 mole. I'm going to just leave that in the exact value for now, okay? And once you get it there, this is giving you the 18 degrees Celsius and 99.85 kilopascal will be produced. So before we move on to that, actually, we got to think about the reaction ratio between copper. So according to the reaction ratio of copper, bit of stoichiometry, and to the what was it, NO, which is 3 to 2. This is what I recommend all the times, so that you get the 3 of the N and O is therefore 2 of the N of this copper. Therefore, what you get? The number of mole of the nitrogen monoxide must be 2 on 3 of the N of the copper. That is times 2. So 2 on 3 times that 2.20 divided by 63.55 there. I'd rather leave that in some exact value for now, just for now here. Okay, well, this is kind of giving you like 0.0, let's write that, 0.0231 mole, but you can calculate the exact values. Now, the pressure is given as 99.85 kilopascal. Temperature is given as 18 degrees Celsius. Check the units, kilopascal, fine, but degrees Celsius must be converted into the Kelvin by adding 273.15. So you get 291.15 Kelvin. Therefore, final stage, the volume from the PV equals to nRT can be found by nRT over P. The N is given as 0.0231, or exact values you had, times the 8.314, times the temperature, that's a 291.15, divided by 99.85, like this. Your final answer, therefore, should be 0.559 liter, which is 559 milliliters. Given sigfic of, we have 4 and 3, so it's 3 sigfics in this case. B, if the copper is reacted with the concentrated nitric acid and a different reaction occurs at the nitrogen 4 oxide, NO2 is produced, which is given as a formula there. Now calculate the volume of the NO2 produced at 25 degrees Celsius and the pressure at 102.0 kilopascal if the 2.2 grams copper is reacted again. All right, and then with the excess of this concentrated nitric acid. So start it again, we got to start with the N of the copper with same as the previous one, mass of the molar mass. That'll be 2.20 divided by 63.55. We're going to start from this over here. Okay. Now, now we got a new reaction ratio, so let's write it down. According to the reaction ratio of copper to the, what we're looking for is NO2. NO2 is given as 1 to 2. It's actually simpler reaction ratio. Therefore, N of the NO2 is simply 2 times N of the copper. That is 2.20 divided by 63.55. Okay, so that'll be 4.40 divided by 63.55 mole in exact values. Okay, after that, you got to recalculate the volume. So the temperature is given as 25 degrees Celsius. That's basically adding up to 298.15 Kelvin. Pressure is given as 102.0 kilopascal. Okay, just by looking at the temperature pressure, this is something that's very close to the SLC, but not quite that in the SLC. SLC means 100 kilopascal with standard. So if you have 102, you can't use that molar volume. In other words, you have to use the ideal gas flow again. So volume, again, is equals to nRT over P. That would be N, that's a 4.40 divided by 63.55. That times the 8.314 times the temperature, 298.15, and divided by 102.0, like this. Then your final answer must be 1.68 liter for the final answer then. That's for question 2. 3. A helium balloon is to be used to carry scientific instruments into the upper atmosphere. At the ground level, the balloon has the volume of the 15 liters at the temperature of the 20 degrees Celsius and the pressure of the 752 millimole mercury. What will be the volume of the balloon when the temperature is minus 25 degrees Celsius and the pressure is 100 millimeter mercury? Now, as I said, you have something that given initially, and you have a change. Then you're maybe not using the ideal gas flow. You don't have to use that. You can, but it's got to be a little more complicated if you decide to use that. So you have to use the combined gas flow. When do we not use the combined gas flow? Because you see that there are 2 factors of the gases that change. 1, the temperature, 2, the pressure. And the question is asking you to find the volume. So that's clearly indicating that we can use combined gas flow, which is P1 V1 over T1 equals to P2 V2 over T2. If you started looking for, I mean, I can prove that even using the ideal gas flow, that PV equals nRT means that PV of nRT, you have the N and R are basically the constant values in the given here. Because even though you go into different like the pressure and the volume, you don't really change the number of moles inside. Means that N and R can be cancelled, basically giving you the combined gas flow from that too. But the reason why I prefer the combined gas flow is because I don't need to go through that complicated unit conversions. Except one. You still need to convert the unit of temperature to the Kelvin because we have simply have a minus there. We cannot have the negative volume, guys. Remember, we can't have negative volume. This is not possible to get negative volume. There's a quantity. I can't have the negative volume. So this is why you need to convert the temperature, T1, which is 20 degrees Celsius into the Kelvin. That's a 298.15 Kelvin. T2 would be then minus 25 degrees Celsius, 278. That you get 248.15 Kelvin like this. This is the only process you need to do, the only unit conversion you need to do, and then substitute all the values in. You get the V2 is therefore P1 V1 over T1 times that, V2 T2 over P2 like this. The P1 that we have, the pressure one, that's given us 752. Don't need to convert the unit back in here, just leave that the millimeter mercury, same unit, times the volume of the 15 divided by T1, 298.15. That times that, the temperature of 248.15 divided by the pressure 200. Then you'd get 1.68 liters straight away. Even like after you decided to like an ideal gas law, you actually get the same answer. But this is important that there are 3 marker questions in the exam. Guys, the amount of time you spend for every mark, each mark in general, is you just times the 1.5. So if you have 3 marks, the approximate time you spend for the 3 marker is 4.5 minutes within 5 minutes, including some reading time. If you decided to use the combined gas law, I'm sure that it will take more than 5 minutes to solve that question. But if you're just using the combined gas law like this, it takes me like 2 minutes, maybe 1 minute for me, like maybe 2 minutes for you. Okay, so this is why you need to choose the methods correctly. Sometimes examiners, markers will not want to see that combined gas law because that question is designed for the ideal gas law. The question is designed for the combined gas law in that case. And Kristen, this is why I re-ask you. Are you sure? Okay, you can, but that takes some more time. Save your time. Time is very important. You only get a 1 hour, 2 in the exam. You need to think about how you're going to efficiently finish the paper and get the best mark. All right, could you try that in question 4, please? There are some questions. This is some interesting question you can try. I'll give you about 9 marks. You have 10 minutes. Okay, question 4. Let's do it. A. Use the expression PV equals to nRT to calculate the molar volume of the ideal gas at 20 degrees Celsius and a pressure of the 101.3 kilopascal. So, guys, remember the molar, the term molar volume. It tells you that, it's always telling you that the volume for 1.0 mole of, or the, it's kind of, yeah, 1.0 mole or per mole of gas. Per mole of the gas, I should say, like per mole of the gas. And this is why the unit is given as liter per mole, given here like this. In other words, if you want to find the molar volumes, we just got to make that N to be 1 in that case, because we want to find that the volume for given 1 mole of the gas. And rest, we're given that the temperature given at 20 degrees Celsius, converted back into the Kelvin, which is 295. Let's check it again, 293.15 Kelvin. That's for the temperature. Now for the pressure, that would be 101.3 kilopascal. That's basically 1 atmosphere. And the rest is something we have to find. So from the PV equals to nRT, then V would be nRT over P. The N, we now set it to the 1 per mole times R 8.314 times the temperature. We found 293.15 divided by 101.3 kilopascal. Then you should get 24.05 liter. That's basically a volume of 1 mole. So you can write it down. This is that. Okay, it's a per mole, by the way, then. It means that by increasing the number of moles, you're increasing the volume as well, too. That's according to Avogadro's law. B. Use the form, the value from the part A to calculate the density in grams per liter of nitrogen ammonia there. So, okay, like that. Now, consider that like how we're going to get the density values. So, guys, here we have the gram per liter. This is what we want to get. This is what we want to get. What you're given there is you're given liter. You're given liter per mole. That's your given. So first, if I'm asking you, hey, I want to get the conversion, like the unit conversion from liter per mole to gram per liter. Don't just change that. There's a liter per mole means that we have this much of volume per mole. In other words, if you want to get into the mole per liter from here to there, you go to reciprocal, basically divided by 1 on something of that, the volume. Does it make sense? Okay, and then from mole to gram, how to convert that? Mole to gram, N to the M relationship, you just need to times the molar mass of it too. A little tricky because it's not usual that we get a unit conversion like that, but you have to think about how we're going to convert the unit, therefore how it's going to affect the everything. So can we say the density then? Density of the nitrogen. Remember that nitrogen doesn't come in the monoatomic, it always comes to N2. Always coming into the diatomic forms. Even though they don't really say that nitrogen gas, it basically comes in diatomic. That's something we learned in module 1. Then, we may consider that it's got to be what? Molar mass divided by the molar volume is something that we can consider from the unit conversion from liter per mole into the gram per liter. Does that make sense? That means molar mass of the N2, that's the 2 times 14.01 on the top. And the molar volume, we found that at 24.05. This will give you then 1.165 gram per liter straight away. Okay? Or you may just convert the units, like do the same thing, but you gotta get the same result. Density of the ammonia is NH3. So that's basically saying molar mass divided by molar volume. That is 14.01 plus 3 times 1.008. That divided by 24.05 like that. Then you get 0.709 gram per liter as well. Then lastly, density of the nitrogen 2 oxide, NO2, that's the nitrogen dioxide. We can, sorry, nitrogen oxide should be just NO. Taking that nitrogen to be 2 plus, oxygen be 2 minus. They're having 1-to-1 ratio. Then, same molar mass on the molar volume that we have nitrogen 14.01 plus 16, oxygen divided by 24.05. Then you should get the 1.248 gram per liter. Everything in the 3 decimal points then. All good? Okay. All right. The actual densities of the 3 gases at 20 degrees and the pressure of the 101.3 kilopascal are given in the table below. Nitrogen is that 1.165 and this ammonia and nitrogen oxide. So nitrogen 1.165, which is kind of matching to that density, which is good. But for the ammonia, we are given 0.709. We calculated, but the actual density was 0.717. Okay, and then nitrogen is given at 1.249. That's actually what we measured practically. That's a theoretical, that's a practical data. Then we got to think about, because that's for question day, we got to think about what makes the difference between those theoretical and practical data later on. Let's do the C first. From that given densities, if you want to get into the molar volume, then what do? It's molar volume is then, we're going backwards. Like this. That means you divide that with the molar mass, okay, and times that, and kind of go reciprocal of that. So to do so, it's got to be going to given volume density. So density 1.165. Hang on, and it would be just the volume. Hang on, are we given the molar? Oh yeah, it'll be this. The molar mass divided by, in that case, of the densities. Is how we can get the molar volumes too. Then molar volume of the N2 would be molar mass 22 times 14.01. That divided by, given the mass volume, the volume 1.165 basically, still giving you that 24.05 liter per mole. Okay, so unit conversion again, so we're going backwards from here, reciprocal of that. Volume of the NH3 is then 14.01 plus 3 times 1.08, that divided by the given density value 0.717. Then you get the actual volume of the gas at 23.77 liter per mole. The volume of the NO, nitrogen monoxide, would be 14.01 plus 16. That divided by density 1.249. As a result, you'd get 24.03 liter per mole. Now, what we need to compare from here at this point is the actual molar mass for the elder gases, we found that 24.05. So compare that. This is basically same as 24.05 liter per mole. This is less than the gas volume that what we calculated. Is also less than this. Slightly, but yes, still there are some. There's a bit of a change, but yeah, slightly changing that too. Then the question is this: what causes them to have the different volume? This is the scientific skills questions. Okay, and I picked that this is kind of interesting question. You actually need some understanding of intermolecular forces here. Okay, Jenny, we have an N and N. First, what is the bonding between nitrogen and nitrogen? Non-metal, non-metal bonding. Come on, you have a test coming. Non-metal and non-metal. Huh? What was it again? That's my question. What is it again? Okay. Anyone? What's the bonding between non-metals and non-metals? It's called the covalent bondings. Okay. And we learned that depends on their electronegativity. Depends on how strong they are. They can equally or unequally share the electrons. In between nitrogen, they're identical basically. So they're equally sharing the electrons. So in terms of molar, intra, they're carrying the non-polar covalent bonding. This means that there is no dipole. Study that, you will get these questions a lot. Not only for year 11, year 12. Oh yeah, you will see these till you finish HSC. Yeah, a lot. Lots of those. We did that on Thursday. We got to do it in the organic chemistry. There are no dipoles. Means that the only intermolecular force they carry is the weak dispersion force, which is known as the weakest. We don't really count that. That means that weak means in between the nitrogen to nitrogen, these two have a kind of really weak interaction or weak attraction between them. So this is the reason why when we calculate that without calculating any other factors, the volume of the nitrogen gas is exactly matching to what we calculated, because it doesn't carry that much greater like forces or like attraction between them. However, NH3, trigonal pyramidal shape, which has the partial positive, partial negative charges. What do you call this? Is due to the polar covalent bonding. Why is that? Because the electronegativity difference between the hydrogen, I told you like the hydrogen carries the least, the weakest electronegativity. Nitrogen carries one of the greatest, the highest, the electronegativity. Means that due to the unequal share of the nitrogen and hydrogen, they have formed the polar covalent bondings, and these is now known as a dipole are formed. Then, if we have another nitrogen or the ammonia there, you just see that partial negative and partial positive are closely packed together. This is known as dipole-dipole attraction. But among that, the bonding between nitrogen and hydrogen, this is forming the strongest dipole-dipole, which is called the hydrogen bonding. What is the hydrogen bonding means? What does that mean? It means that ammonia love to attract kind of more packed and more dense together more easily compared to the nitrogen gas. This means, it's kind of explained in why that ammonia gas is actually much denser, or like a smaller value. That's kind of giving it because of due to the hydrogen bonding, the ammonia gas is kind of more packed together, therefore carries the smaller volume than what we expected. Again, where do we learn that? Module 1. What is this question? Module 2. Do you think you're going to get this question half yearly? You're going to get these type of questions half yearly then. Combine module 1 and 2. So you're going to need to think and process that, how you're going to combine, how you're going to get the combined question of module 1 and 2. If I picked one of the hardest questions in like an elder school exam, this is one of the most difficult questions you can get. But it's quite straightforward using that. What about between nitrogen and oxygen? They are having kind of similar electronegativity, not as much as the nitrogen. So they'll be slightly polar, or they're carrying the greater intermolecular force than the ammonia. So you wouldn't see much change. It's only be like 0.02, but which kind of tells us that the intermolecular force of the nitrogen oxygen is slightly greater than intermolecular force between the nitrogen and nitrogen. Please remember this, intermolecular forces, not only for year 11, for your yield exam. Yes, you will get one. Your HSC, you get 2 questions at least about the intermolecular forces. At the time, you're going to more deal with organic chemistry though, but you got the exact same working out for that. So those who actually understand what the intermolecular force and thinking about the the consequences having to carry integrate intermolecular force, you would have found that year 12 content's got to be so easy. Like you're like, okay, I'm learned that in year 11. I don't need to spend too much time on that. You actually feel like that. Okay, that's how you manage your time in year 12. Anyways, that's the answer for the this question too. Study that. You get these. Any questions? Nope. Okay, that's all for today. I mean, then I'll need to collect your homework and give us a new homework set for next week. As I said, we are going to have a test next week. So Jenny, you're going to have a test next Monday. Unless you're coming back on Saturday.